In quantum mechanics, there is an important operator which is the angular momentum, but we will also see that there is another operator which is the square of the angular momentum. We will see why. The square of the angular momentum is defined as Lx squared plus Ly squared plus Lz squared. Let me zoom out a little bit. And Lx squared, Ly squared and Lz squared, they are just three angular momenta, Lx, Ly, Lz, which can also be called L1, L2, L3. And in classical physics, the angular momentum for a particle, usually it's calculated with respect to a point. You have the position vector, which I can call r, and then I take the cross product with the momentum p. Okay? From here, we can generalize this expression to quantum mechanics. So the ith component of angular momentum is given by Levi-Civita symbol, epsilon ijk, which is used for cross products. And then I have xj, which is the jth component of the position, which I could also call x instead of r. And then I have momentum in quantum mechanics is the derivative with respect to k, and then I also have a constant minus I h bar, which is not important conceptually, but we will stick to that. And let me use some kind of weird numbering of my equations. I will call this equation 176, and this is due to the notes that I have. So these numbers, as I said some time ago, might not really be in increasing order, okay? But what matters is that this number here is not equal to any other number that I've used before. So if you want to refer to this equation, you might do so without any kind of ambiguity. That's the important thing. So I'm sticking to my notes anyway. And I will call this equation 177. You could substitute these expressions in the angular momentum, and this derivative is of course a derivative with respect to xk. Okay, that's an upper index, but in this case we are using quantum mechanics, so if I use an upper index here or a lower index, since we are in 3 dimensions now, these two operators are exactly the same, because the metric in 3-dimensional space is Euclidean. We have the Kronecker delta, so our metric tensor is just a Kronecker delta, so we are in 3-dimensional space. And you could also find an expression for L squared by using polar coordinates. So if you switch to polar coordinates, you can find an expression which we will not use. But just to show you that it's kind of a complicated expression, which in principle you can derive just by using calculus, concepts of calculus, derivatives, and so on and so forth. You have minus h bar squared, 1 over sine theta, d theta, sine theta, d theta, plus 1 over sine squared theta, d with respect to phi, and this is 178, let's say. This is just an expression which we will not use. It's used when you consider polar coordinates. We will not use this expression. This is just for the sake of showing how complicated it can be also in polar coordinates. I mean, this is not a very simple operator in general. From this expression here, Li, you can also try to derive the commutators, for example, between Lx and Ly. And you can find that this is equal to I h bar Lz, and also Lz Lx is equal to I h bar Ly, and Ly Lz is equal to I h bar Lx. And these commutators are very important. And you can see that since these commutators are non-zero, the angular momenta do not commute. It means that they cannot be measured simultaneously. Okay, 179, let's say. But there is another commutator which you can find. For example, the commutator between L squared with Lj. This commutator, you can find that this is equal to 0. That's why L squared is very important, where in this case j can be either equal to 1, 2, 3. So it can be measured simultaneously with either Lx, Ly, or Lz. That's why L squared is very important. Now we will define other two important operators which will be useful. I will define L plus as Lx plus I Ly, and I will define the operator L minus equal to Lx minus I Ly. Notice that if you take L plus dagger, you take the dagger of L plus, you will get Lx dagger, and then you have minus I Ly dagger. But Lx and Ly are Hermitian operators because they are related to momentum, angular momentum. So you can measure angular momentum, its eigenvalues are real, therefore you have Lx minus I Ly, which is equal to L minus. Okay? This is something important to notice. Now from 180 and 181, you can derive that the commutator between L squared and L plus is equal to 0, and the commutator between L squared and L minus is also equal to 0. Okay, so this is 183. And also you can also find the commutators between Lz with L plus, which is equal to h bar L plus, and also the commutator between Lz and L minus, which is minus h bar L minus. Now our aim is to try to build the eigenvalues and the eigenfunctions of the operator L squared. So we want to find the eigenvalues and eigenfunctions of L squared and Lz. Let YLM, it's a function which depends on two indices, L and M, and we assume this to be an eigenfunction of L squared and Lz, because remember, L squared and Lz, they commute, right? So if they commute, they can share the same eigenfunction, and that's why I'm using also two indices to denote the eigenfunction, because in principle we can have an eigenvalue which is related to L squared and an eigenvalue which is related to Lz. Now let's try to evaluate L squared YLM. So by definition, since YLM is an eigenfunction of L squared, we can define this to be some eigenvalue here multiplied by YLM. And now I can define an eigenvalue by using, for example, either the index L or the index M. I will choose the index L, and I will define it to be h squared L times L plus 1. Okay, this is just for convenience. Equation 185. And also I can define the eigenvalue for Lz. So Lz times YLM is equal to h bar M by definition. So this is a definition, okay? H bar M times YLM, 186. Now I want to compute another quantity. So we want to understand something more about these parameters M and L. We want to know something more about them. Now let's compute L squared L plus YLM. So we are acting first with the operator L plus on YLM, and then we are acting with L squared. We know that L plus and L squared, they commute if you go back and check 183. So I can also rewrite it as L plus L squared YLM. And when I act with L squared on YLM, I will get the eigenvalue. So this will be equal to h squared L plus 1, and also I will act with L plus on YLM, right? Because this is just a scalar, so I can put it before the operator, on the left of the operator. Therefore, it means that if you take a look at it, L plus or even minus, because I could do the same thing with L minus as well. I could find the same quantities. So let me put it in red here. Since L squared also commutes with L minus, I could put a minus here as well to denote that the state L plus or L minus YLM is still an eigenstate of L squared. Okay? So L plus or minus do nothing on the parameter L, which is related to L squared. Remember, L is related to L squared. Now, let's compute another quantity, Lz, L plus or minus, so it can be both of them, YLM, and we know the commutation relation between Lz and L plus minus. You can go back and check equation 184. So we can rewrite this as L plus or minus Lz, and then we have plus the commutator between Lz and L plus minus, acting on YLM. This commutator, we know what it is equal to. It's plus or minus, it depends on whether there is a plus or a minus there, and we have H bar L plus or minus. When these operators act on this state here, this quantity will give rise to, because we act first with Lz, so this will give rise to H bar M times L plus minus YLM. So we can find easily that this is equal to H bar times M plus or minus 1 L plus or minus YLM. What this means is that L plus or minus, they increase or decrease according to the plus or minus. So that's why we use the notation L plus or L minus, because they increase or decrease M, the value for M. So we have some kind of ladder of states. We have some maximum value, we will call it M plus, which is equal to the maximum value of M. Then we have other possible values of M here, and we will arrive at some point at some ground state. So we have some M minus equal to the minimum value for M. Now, why does M have an upper bound? Why is there an upper bound? Well, because we can find that H bar squared times L plus 1, which is an eigenvalue for L squared. L squared, if you think about classical physics, this should be always greater than or equal to the square of each component of angular momentum. And if I take the eigenvalue for angular momentum, I have H times M, and if I square it, this quantity remains larger than H squared M squared, right? Therefore, from here we get that if L, for example, is some kind of definite value, we have M is less than or equal to some kind of square root of L times L plus 1. So there must exist a state which I will call YLM plus, let's say. There exists a state LM plus such that when I act with the L plus on YLM plus, I will get 0, because L plus in this case will annihilate that state. Let's find something else which is also meaningful. As I said, if I take L plus YLM plus, I will get 0, but I would also get 0 if I take the dot product with another quantity. For example, let's take L plus YLM plus. So this quantity here is still equal to 0, because the state is by itself 0. But I could also rewrite it like this, so I can rewrite it as YLM plus, and then I will take L plus dagger which is equal to L minus, and then I have L plus, Y, L, M plus, and then this is equal to Y, L, M plus, and then I have, if I take L minus times L plus, and you take a look at the expressions, I will get something pretty straightforward. I will get Lx squared plus Ly squared plus I commutator Lx Ly, and then here I have Y Lm plus, and you can rewrite Lx squared plus Ly squared as L squared minus Lz squared, and this commutator here is just equal to minus Lz h bar. So this quantity will give rise to Y Lm plus, and then when you act L squared, you will get h squared L plus 1, and then when you act with minus Lz squared, you will get minus h squared M squared, where in this case it's M plus because you're acting on Y Lm plus, right? And then you have minus M plus h squared. So in this case the commutator is equal to I Lzh. So when I multiply by I will get a minus. Okay, I Lzh, when I multiply by I will get a minus. So I have minus mh h bar squared, and here I have Y Lm plus. And of course, if these states are just unit norm, so their norm is equal to 1, I will just get h squared L plus 1 minus h squared M plus squared minus M plus h squared. This should be equal to 0. Remember where we started. Okay, so from here you will get that the maximum value for M, which is M plus, from this equation you easily get that M plus is equal to L. So let's call it equation 187. And similarly, it can be proved that M minus is equal to minus L. Okay, 188. Therefore, the ladder of states for M, you have the maximum value, which is L plus L, and then you have other possible values here, and then here you have minus L. And therefore, you will have 2L plus 1 states. For each L, you will have 2L plus 1 states for M, let's say. This quantity here in general should be an integer. Okay, this is an integer. But as you can see, it's an integer even if L is half integer. Right? So M is greater than or equal to minus L, but is less than or equal to L. And so if we, for example, have L equal to 0, the only possible value is M equal to 0 when L equals 0. Right? So we have just one state. Okay, I can put it here. So I have this state here. I will mark the state with a line like this. And if L, for example, is 1/2, I have two states. One here and one here. So this is the state where L equals 1/2. And here M is equal to 1/2. Down here M is equal to minus 1/2. And this is very important because what happens is that this is exactly the state that describes the spin of the electron. But we can have other possibilities. For example, we might have a state where L is equal to 1 and you have this value here, this value. So in this case, you have L equal 1. Here you have M equal to 0. Here you have M equal to 1. Here you have M equal to minus 1. And then you can go on. You have another state like this with 4 possible values for M. These are different states, so I mean, it's not just a state, it's 4 different states because you're changing m. So you have m equal to 3f, m equal to 1/2 here, m equal to minus 1/2, m equal to minus 3f's, and the value for L in this case is equal to 3f's. Okay, now the average value of L squared is equal to the eigenvalue h squared L plus 1, but this is also equal to the average value of Lz squared plus the average value of Lx squared plus the average value of Ly squared. The average value for Lz squared, if you take a look at equation 186, this will be equal to h squared L squared, and these two eigenvalues here, they are equal. So from here you will get 2 times h bar squared L divided by 2 here.